When a new AI model drops, the question that matters for most teams is not the leaderboard score. It is whether your stack can run it reliably, what it costs at your traffic scale, and which shortcuts will break in production. Today, we connect that headline to the engineering trade-offs behind the hype. You are likely treating vector database latency as a compute problem, believing that throwing more expensive GPUs at the issue will solve speed issues. In reality, for massive datasets, the bottleneck is almost always an index graph architecture flaw, not raw processing power. Most production systems rely on approximate nearest neighbor search algorithms like Hnsw or IVF to find matches in vast data lakes. These structures require traversing a complex web of connections known as an index graph. While efficient for smaller datasets, their design forces the system into a memory bandwidth wall as scale increases. The algorithm must dynamically walk through millions of nodes and edges to locate a single relevant vector. As your dataset grows from hundreds of thousands to billions of entries, the number of edges in this graph explodes non-linearly. This creates a scenario where no amount of GPU speed can overcome the time it takes for memory controllers to fetch these scattered nodes from RAM. Engineers often observe high latency and assume they need more powerful inference hardware. They upgrade their server racks with faster chips, expecting linear performance gains. Instead, adding a faster GPU yields diminishing returns because the system is starved waiting for data to move from memory to compute units. You are essentially trying to drive a Ferrari on a road that has been turned into a traffic jam by bad design. The hardware is capable of flying, the index structure is forcing it to crawl. This leads to significant overspending on infrastructure that cannot solve an algorithmic scaling issue because you have misdiagnosed the root cause. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The solution does not lie in buying better silicon, but in shifting from graph-heavy traversal to static semantic graphs or pre-indexed structures. Newer approaches utilize a static map built during initialization rather than dynamic vector traversal at runtime. By pre-computing the relationships between data points, such as code dependencies or document hierarchies, these systems eliminate the need for expensive real-time graph traversals during inference. This allows AI agents to retrieve context with significantly lower latency and fewer token calls because they access a direct map of knowledge rather than searching through a complex web of vector similarities. Recent studies indicate that the time horizon for frontier models to complete complex tasks is currently around 50 minutes, but this capability doubles every 7 months since 2019. As AI systems take on longer, more intricate jobs over the next 5 years, they will demand massive context windows and rapid retrieval speeds. Current vector database architectures struggle to maintain speed as these contexts expand, exacerbating the graph traversal bottleneck just when you need it most. Tools utilizing static graphs have already demonstrated fewer tool calls and reduced latency for complex coding agents compared to traditional methods, proving that structural changes outperform raw compute scaling in specific retrieval scenarios. However, this is not a call to abandon vector search entirely. Dynamic data still requires the flexibility of approximate nearest neighbor algorithms when relationships are unknown or constantly shifting. The key is making an informed architectural judgment based on your specific use case. If you're designing a system where speed is critical for real-time applications like enterprise RAG, assuming that more GPU equals faster will lead to budget overruns and dead ends. You must audit your indexing strategy before upgrading any hardware cluster. The distinction between compute-bound inference problems and memory bandwidth-bound graph traversal problems is the difference between solving a bottleneck or just ignoring it. Senior engineers who understand this separation can make smarter decisions about when to switch data structures entirely versus when to invest in faster chips. This ability to diagnose whether latency stems from algorithmic complexity or processing power is a high-value skill that separates those who simply add resources from those who optimize the system design for long-term viability. If you are currently relying on Hnsw or IVF on massive datasets, check if graph traversal latency is your true culprit before ordering new servers. Consider static semantic graphs for use cases where relationships between data points are known and stable, as this can reduce hardware costs while improving response times for AI agents. The bottleneck isn't your GPU's speed. It is the time your memory controller spends fetching nodes from a sprawling index that was never designed to scale efficiently without paying an exponential price in bandwidth. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.